There is a number buried in the heart of every star that has ever made carbon that seems to sit exactly where it needs to sit. Not close, not roughly, almost exactly. And tonight, we're going to wander slowly through why that number, and dozens of others like it scattered across the laws of physics, have kept scientists a little bit puzzled for the better part of a century. Let's start in the 1950s with a British astronomer named Fred Hoyle, who was thinking quietly about something that should have been simple. Stars make elements. Everybody agrees on that. Hydrogen fuses into helium, releasing the light and heat that make a star shine in the first place. That part of the story is calm and well understood. But Hoyle was looking a little further down the chain, at how a star goes from helium to something heavier, and he noticed that the numbers didn't want to cooperate. Here's the trouble. To build carbon, a star needs to fuse 3 helium nuclei together, but nature doesn't do that all at once. It happens in 2 steps. First, 2 helium nuclei collide and fuse into a nucleus called beryllium-8. Then, if a third helium nucleus happens to come along in time, it can fuse with that beryllium to finally make carbon. The problem is the word "in time." Beryllium-8 is desperately unstable. It falls apart in about 10 to the negative 16th of a second, which is a tenth of a quadrillionth of a second, an interval so short it barely deserves to be called a moment at all. For a third helium nucleus to fuse with it, that collision has to happen inside that impossibly brief window. When physicists worked out how likely that was, using the ordinary rules of nuclear reactions known at the time, the answer came out far too small. According to the physics as it was understood, stars should be manufacturing almost no carbon at all. And yet carbon is everywhere. It's the 4th most abundant element in the entire universe, after hydrogen, helium, and oxygen. It's the backbone of every organic molecule, every strand of genetic material, every one of us. So something was clearly wrong with the calculation, not with the universe. Hoyle's insight was to ask a slightly unusual question. What if there were a hidden shortcut? In nuclear physics, certain combinations of particles can briefly settle into what's called a resonance, an excited, unstable arrangement that acts almost like a stepping stone, making an otherwise unlikely reaction far more probable. The way a narrow bridge across a river makes a crossing possible that would otherwise require swimming against a strong current. Hoyle reasoned that if carbon-12 had a resonance sitting at just the right energy, close to 7.68 million electron volts above its ground state, it would dramatically raise the odds of that third helium nucleus finding its way in before the beryllium fell apart. At the time, this was a strange thing to propose. Nobody had measured any such resonance. There was no direct evidence for it. Hoyle was essentially arguing backward from the fact that we exist, and that carbon exists in abundance, to the conclusion that a very specific and previously unknown detail of nuclear structure had to be there, waiting to be found. He was visiting the California Institute of Technology at the time, and he took his idea to the experimental nuclear physicists working there, urging them to go and look. It wasn't an easy sell. Searching for a resonance at a precise, previously unpredicted energy, based on nothing but an argument from cosmic abundance, is not the kind of proposal experimentalists receive every day. But they ran the experiment anyway, using the machinery at the Kellogg Radiation Laboratory, and they found it. A resonance in carbon-12, sitting at about 7.65 million electron volts, within about 0.5% of Hoyle's predicted value. It's known today as the Hoyle Resonance, and it remains one of the most striking examples in the history of physics of a prediction made not from first principles, but from working backward from our own existence. Without it, the numbers say stars would make almost no carbon whatsoever. Nudge that resonance up by only a few percent, and carbon production collapses. Nudge it down by a similar amount instead, and something almost as strange happens. Stars do make carbon, but hardly any oxygen because without a companion effect, a similar near absence of a resonance in the reaction that would otherwise convert carbon into oxygen. All of that freshly made carbon keeps getting burned away into something else. It's as if two separate dials, one in carbon, one in oxygen, are each set to produce exactly the balance of these two elements that turns out to be so essential for chemistry, and eventually, for life. This isn't an isolated oddity. The more physicists have looked at the fundamental rules underlying our universe, the more they keep finding numbers that seem to sit in unusually narrow, favorable ranges. Values where a slightly different setting would mean no complex chemistry, no stable stars, no galaxies, and as far as anyone can tell, nobody around to notice any of it. It shows up again and again, in different corners of physics that don't obviously have anything to do with each other, and it raises a question that scientists still don't have a settled answer to. So let's slow down and go looking for a few more of these dials, one at a time, and see what happens when you imagine turning them. To understand why the Hoyle resonance is just one example among many, it helps to understand what a physical constant actually is, and why physicists find them so strange to think about. Every equation you learn in a physics class, from the way objects fall, to the way planets orbit, to the way atoms hold together, has numbers built into it that aren't determined by the equation itself. Isaac Newton gave us a beautifully simple law describing how gravity pulls two masses toward each other, and Albert Einstein later refined that picture into general relativity, describing gravity as the bending of space and time itself. But neither of those theories on their own tells you how strong gravity actually is. For that, you need a number, usually called big G, the universal gravitational constant, and there is no way to derive it from pure logic or pure mathematics. It simply has to be measured by going out and asking nature directly. The person who first managed to measure it was a reclusive English scientist named Henry Cavendish, working in 1798, decades before anyone fully appreciated what his experiment would come to mean. Cavendish built an apparatus with two small lead spheres hanging from a thin torsion wire, delicately balanced so that even a tiny force would cause the wire to twist. Then he brought two much larger lead spheres, each weighing about 350 pounds, close to the small ones, and waited to see whether gravity alone could pull the small spheres toward the large ones enough to twist the wire measurably. The force involved was almost unbelievably faint, comparable to the weight of a speck of dust. Cavendish had to house the entire apparatus inside a sealed shed and observe the twisting of the wire from outside, through a telescope, because his own body heat, simply by standing near the device, would stir the air enough to swamp the signal he was trying to measure. By carefully tracking how far the wire twisted, he was able to work out the strength of gravity for the first time in human history, giving physicists their first real handle on the value of that constant hiding inside Newton's elegant equation. Now here's a subtlety worth pausing on. The particular number you get for the gravitational constant depends on which units you use, meters, kilograms, seconds, all of which are human inventions, chosen somewhat arbitrarily over the centuries. So in one sense, the specific numerical value isn't fundamental at all. It's just a byproduct of our choice of measuring sticks. But physicists have found ways to combine different constants together into pure numbers that don't depend on any human unit system whatsoever. Ratios that would come out exactly the same whether you were a human on Earth or some entirely different kind of being on the far side of the galaxy, using whatever units it preferred. One of the simplest examples is the mass ratio between a proton and an electron. However you choose to measure mass, the proton turns out to be about 1,836 times heavier than the electron. That number doesn't care what units you use. It's just a pure, dimensionless fact about our universe. And it turns out there are roughly 30 of these fundamental, unit-independent numbers scattered throughout physics, each one a kind of dial that our best theories simply cannot predict or explain. They aren't outputs of some deeper equation. They're inputs, values that had to be measured because nothing in the mathematics forces them to be any particular way. And once you accept that these numbers are, in some sense, free parameters of nature rather than logical necessities, a very natural question follows. What would happen if they were even slightly different? What kind of universe would you get if you reached in and nudged one of those 30 dials just a little? So let's turn a few of them, one at a time, and see what happens. Let's start with a very small number that turns out to matter enormously: the mass difference between a neutron and a proton. In our universe, a neutron is very slightly heavier than a proton, by about 1.29 million electron volts, which works out to roughly 0.14% of a neutron's total mass, or the equivalent of about 2.5 electron masses. It sounds like a trivial difference, almost not worth mentioning. But that tiny gap has an outsized consequence. Because the neutron is heavier, a free neutron sitting on its own is unstable and will eventually decay into a proton, an electron, and a nearly massless particle called an antineutrino. A free proton, on the other hand, is stable indefinitely. Now imagine flipping that relationship, making protons even slightly heavier than neutrons instead. In that universe, the reverse would happen. Protons would decay into neutrons, absorbing nearby electrons in the process. Every hydrogen atom in existence, which is just a single proton paired with a single electron, would eventually vanish, converting into a neutron. A universe like that would never build the rest of the periodic table. No hydrogen means no water, no stars that shine the way ours does, no chemistry as we understand it, nothing but a slowly darkening expanse of neutrons, largely inert, doing very little of interest. All of that hinges on a mass difference so small it took physicists decades of careful measurement to pin down precisely. And yet, if it had gone the other way, or even landed much closer to zero, the universe as a stage for chemistry would likely never have gotten off the ground. Let's turn a different dial. The strength of the strong nuclear force, the force responsible for holding the nucleus of an atom together against the electrical repulsion that would otherwise blow it apart. The very first step in the chain of reactions that powers our sun involves fusing two protons together into a nucleus called deuterium, which is essentially heavy hydrogen, a proton bound to a neutron. That bond is not particularly strong. Deuterium is held together by a binding energy of only about 2.2 million electron volts, a fairly modest amount as these things go. If you weaken the strong force by just a handful of percent, that binding disappears, deuterium becomes unstable, and the entire fusion chain that powers stars like our sun simply never gets started. No fusion means no long, steady release of energy from stellar cores. No factories cooking hydrogen and helium into the heavier elements that eventually spread across the universe as stardust. No long-lived, stable stars providing the gentle, sustained warmth that a planet needs over billions of years to let complex chemistry, and eventually life, slowly unfold. Weaken the strong force by only a small amount, and you don't get a slightly different universe. You get one with no stars at all, in any meaningful sense. What you find, again and again, as you go through this exercise one constant at a time, is that it's remarkably easy to build a universe that simply doesn't work, one that never develops the kind of complexity needed to encode information, form structure, or support anything like life. And that raises an obvious question. We happen to live in a universe where the settings landed in the narrow range that allows for all of this. Is that telling us something? Is there some deeper reason our particular universe turned out this way? Or is it simply that we couldn't be having this conversation in any of the other, less fortunate arrangements? Let's look at one more force before we move on, because it involves a mismatch so large it's almost hard to picture. Gravity, compared to the other fundamental forces, is astonishingly weak. A small refrigerator magnet can lift a paperclip off a table, overpowering the gravitational pull of the entire planet Earth beneath it. If you compare the electric repulsion between two protons crammed together in an atomic nucleus to the gravitational attraction between those same two protons, the electric force wins by a factor of about 10 to the 36th power, which is to say, roughly a trillion times stronger. Nobody fully understands why gravity is so feeble compared to its counterparts, but we can still ask what would happen if it were stronger. Suppose you dialed gravity up by a factor of 1,000,000, which sounds like an enormous change. But even after that adjustment, gravity would still be far weaker than the other forces, roughly 10 to the 30th instead of 10 to the 36th power weaker than electromagnetism. And yet, in a universe with gravity strengthened by only that much, stars would burn through their fuel far more quickly, living for something like 10,000 years instead of the 10 billion years or so that stars like our sun enjoy. 10,000 years is nowhere near enough time for slow processes like planet formation, chemical evolution, and the gradual emergence of complexity to play out. Even this comparatively modest adjustment to one of nature's weakest forces would likely foreclose the possibility of anything like us ever coming to exist. Let's turn one more dial, and this one comes with a genuinely strange story attached to it, stretching back more than 100 years. In 1929, the astronomer Edwin Hubble made an observation that reshaped cosmology. By carefully measuring the light coming from distant galaxies, he found that they were all moving away from us, and that the farther away a galaxy was, the faster it appeared to be receding. The natural conclusion was that the universe itself is expanding, carrying galaxies apart from one another as space itself stretches. For decades afterward, the expected story was straightforward. The universe is full of matter, and matter pulls on other matter through gravity. So even though the universe was expanding, physicists assumed that this gravitational pull should be gradually slowing the expansion down over time, the way a ball thrown upward slows as gravity pulls it back. The open question was simply how much it was slowing down, and whether the universe would eventually stop expanding and collapse back on itself, or slow down forever without quite stopping. Answering that question turned out to be extraordinarily difficult, and it took roughly 70 years to get a reliable answer. The method that finally worked relies on a particular kind of stellar explosion called a Type 1, a supernova. These occur when a dense stellar remnant called a white dwarf siphons matter off a companion star it happens to be orbiting. As the white dwarf gains mass, it approaches a threshold known as the Chandrasekhar limit, at around 1.44 times the mass of our Sun, at which point the pressure holding the white dwarf up against its own gravity gives out catastrophically, and the star detonates. The details of exactly why this happens are their own fascinating story, but the key point for our purposes is that these explosions tend to reach almost exactly the same intrinsic brightness every time, which makes them useful as what astronomers call standard candles. If you know how bright something actually is, and you compare that to how bright it appears from Earth, you can work out how far away it must be, because the apparent brightness of a light source falls off with the square of its distance. So a candle twice as far away looks only a quarter as bright. Separately, by studying how the light from these explosions has been stretched, or redshifted, on its journey to us, astronomers can also work out how fast the exploding star's home galaxy is moving away. In the late 1990s, two independent research groups, the Supernova Cosmology Project, led by Saul Perlmutter at Berkeley, and the High Z Supernova Search Team, led by Brian Schmidt working out of Canberra, Australia, set out to use this method to measure precisely how much the expansion of the universe was slowing down. Since Type 1a supernovae are rare events in any single galaxy, both teams had to photograph thousands of galaxies, wait several weeks, photograph the same patches of sky again, and then use computers to subtract the old images from the new ones. watching for any new point of light that appeared where nothing had been before. A telltale sign of a fresh supernova. What both teams found, independently, stunned them. The expansion of the universe wasn't slowing down at all. It was speeding up. Both teams initially suspected they had made some kind of measurement error because the result ran completely counter to expectations. But the finding held up under scrutiny, and it implied that something is actively pushing the universe apart, not merely failing to counteract gravity, but overpowering it entirely. Scientists began calling this mysterious pushing effect dark energy, and more than 2 decades later, we still don't have a settled explanation for what it actually is. In 2011, Perlmutter, Schmidt, and their colleague Adam Rees were awarded the Nobel Prize in Physics for the discovery. But the idea of some kind of cosmic pushing force actually has a much older history, dating back to Einstein himself. In 1917, Einstein ran into a problem with his own equations of general relativity. Left alone, the mathematics implied that the universe should either be expanding or contracting. It couldn't simply sit still. But at the time, essentially everyone, Einstein included, assumed the universe was static and eternal, neither growing nor shrinking. So Einstein added an extra term to his equations by hand, a kind of built-in anti-gravity baked into the fabric of space itself, carefully tuned to hold the universe motionless. He called it the cosmological constant. There's a popular story that Einstein later called this addition his biggest blunder, and that phrase gets repeated constantly, but historians have had trouble tracing it back to any first-hand quote from Einstein himself. It seems to trace mostly to a 1970 book by the physicist George Gamow, along with a handful of second-hand recollections from other scientists who claim to have heard Einstein say something along those lines. What we do have, in Einstein's own words, is a letter he wrote to the physicist Georges Lemaitre, in which he confessed a long-standing discomfort with the whole idea. He wrote that ever since introducing this extra term, he had always felt uneasy about it, that he found it deeply unsatisfying for the law of gravitation to be built from 2 logically unrelated pieces simply stitched together by addition, and that he could not bring himself to believe something so inelegant could actually reflect how nature truly works. Which makes it something of an irony that this inelegant thing does, in fact, seem to be built into nature. The cosmological constant is real. It exists, and much like the Hoyle Resonance, it appears to be fine-tuned to a startling degree. So what could dark energy actually be? There's one obvious candidate rooted in quantum physics. If you take a box, remove every single particle from inside it, and cool it down to absolute zero, you might expect to be left with nothing at all, a perfect vacuum, empty in the fullest sense of the word. But quantum field theory tells a different story. Even a perfect vacuum still seethes with activity at the smallest scales, pairs of particles flickering briefly into and out of existence, a kind of restless background energy woven into the structure of empty space itself. That vacuum energy is exactly the sort of thing that could, in principle, push space apart, which makes it a tempting explanation for dark energy. There's just one enormous problem with this idea. When physicists use quantum field theory to calculate how much vacuum energy empty space ought to contain, and then compare that prediction to the actual amount of dark energy, we observe pushing the universe apart. The two numbers disagree by a staggering margin, roughly 10 to the 120th power. That is an almost incomprehensibly large discrepancy, so large that it has, somewhat wryly, been called the worst prediction in the history of physics. And here's where things circle back to fine-tuning once again, because the actual measured amount of dark energy in our universe also appears to sit in a narrow, favorable range. If you imagine cranking up the amount of dark energy by even a modest factor, say 100 times its observed value, something dramatic happens to galaxy formation. Ramp up the outward push of dark energy that much, and the expansion of the universe accelerates so quickly, so early, that matter never gets the chance to clump together into large structures at all. Instead of galaxies like our Milky Way, with its hundreds of billions of stars spread across a vast, comparatively calm disk, you'd end up with small, dense, compact little pockets of galaxies instead, crowded regions where supernovae, black holes, and other violent events are packed uncomfortably close together, not unlike the chaotic environment near the very center of our own galaxy, which is itself thought to be a poor location for anything like a stable, life-bearing planetary system, simply because there is too much violent activity crammed into too small a volume. Now, a factor of 100 might sound like an enormous amount of wiggle room. But remember, the theoretical prediction for vacuum energy was off by a factor of 10 to the 120th power. Against a range that vast, a factor of 100 is a vanishingly small sliver, practically nothing at all. There is a little bit of give in exactly how much dark energy a habitable universe can tolerate, but compared to the full range of values the mathematics allows in principle, that give is almost non-existent. One of the more remarkable episodes in this whole story involves the physicist Steven Weinberg, who in 1987, roughly a decade before dark energy was actually measured, made a genuinely bold prediction. Weinberg reasoned that since we exist, and since galaxies of a reasonably large size clearly exist too, the universe's dark energy density couldn't be arbitrarily large. It had to be small enough to allow galaxies to form in the first place, but he argued it was unlikely to be exactly zero either. Working from that logic alone, Weinberg predicted that dark energy should turn out to be small but non-zero, on the same rough order of magnitude as the density of matter in the universe. When the actual measurement came in a decade later, it landed remarkably close to what his reasoning had anticipated. It's a striking example of a scientific prediction built not from a fundamental equation, but from the simple observation that we and galaxies exist at all. There's more to this puzzle than just the constants themselves. It isn't only the dials of nature that seem to be set with unusual precision, but also the starting conditions of the universe as a whole. Our universe appears to have begun in a state of remarkably low entropy, meaning a state of high order, or, put another way, a state with a great deal of usable energy still available to do interesting things with. Over time, according to the second law of thermodynamics, entropy in an isolated system only increases. Things spread out, mix together, and become progressively less ordered. This one-directional drift from order toward disorder is part of why we experience time as flowing in a single direction, from past to future, rather than the other way around. If our universe had instead begun in a high-entropy state, close to maximum disorder from the very start, there would have been very little usable energy left to power anything, no clear gradient driving structure formation, no engine to build stars, planets, or eventually life. Instead, the early universe was born with matter distributed smoothly but not perfectly evenly, just unevenly enough that gravity could slowly draw matter together over time into clumps, and then those clumps into stars, and those stars into galaxies. It was, in effect, born already wound up like a spring, holding a reservoir of potential waiting to be released gradually, rather than all at once. Consider the alternative. If all of the matter in the universe had instead been born already locked away inside black holes, that gravitational potential would have been essentially unusable. You could, in principle, push black holes around or merge them together, but there is very little productive complexity you can build on top of that kind of starting point. The particular way our universe began, ordered just enough to permit slow, gradual structure formation over billions of years, without being so perfectly ordered that nothing interesting ever happens, appears to be yet another feature of our cosmos that looks, on paper, unusually well suited for eventually producing something like us. This same theme even extends to something as basic as the number of dimensions we live in. We experience 3 dimensions of space and one of time. Nothing in the equations of general relativity technically forbids adding more time dimensions, or fewer or more spatial ones. But when physicists have explored what physics would actually look like under different dimensional arrangements, the results tend to be inhospitable. In a universe with only two spatial dimensions, structures as complex as a nervous system, or even simple plumbing like a digestive tract that doesn't divide an organism in two, become extraordinarily difficult to construct. In four or more spatial dimensions, stable, long-lasting orbits, whether of planets around stars or electrons around atomic nuclei, generally stop working, tending to spiral either into their central body or away into the void, rather than settling into the kind of durable, repeating paths that allow solar systems and atoms alike to persist for billions of years. And multiple dimensions of time lead to a set of physical possibilities so strange that physicists have had a difficult time even describing what consistent physical law would look like under those conditions, let alone whether anything resembling a stable, structured universe could emerge from it. The idea of entropy itself has its own long history, worth a brief detour before we move on. The concept was first formalized in the middle of the 19th century by the physicist Rudolf Clausius, studying the efficiency of steam engines, who introduced entropy as a way of quantifying energy that has become unavailable to do useful work. It was the physicist Ludwig Boltzmann, working somewhat later in the same century, who gave entropy its deeper, statistical meaning, showing that it could be understood as a measure of how many different microscopic arrangements of particles correspond to the same overall, large-scale description of a system. A tidy, ordered arrangement corresponds to relatively few possible microscopic configurations, while a disordered, mixed-up arrangement corresponds to an enormous number of them, which is precisely why disordered states are so much more probable, and why entropy tends to increase over time, not because of any strict law forbidding a decrease, but simply because disordered arrangements vastly outnumber ordered ones. The way a shuffled deck of cards is overwhelmingly more likely to look messy than to spontaneously fall back into perfect suit order. This same idea carries an unsettling implication for the very distant future of our own universe. If entropy keeps increasing indefinitely, and current understanding of dark energy suggests the accelerating expansion of the universe will continue essentially forever, then the long-term fate of the cosmos appears to be a slow, gradual spreading out and cooling of everything, stars burning out one by one over trillions of years, black holes themselves eventually evaporating away over timescales almost too large to write out meaningfully, until essentially nothing is left but an extremely dilute, extremely cold, maximally disordered expanse of space, a state sometimes called the heat death of the universe. It's a genuinely distant prospect, unfolding over timescales that dwarf the current age of the universe many times over, and it isn't something to spend much time worrying about on any human timescale, but it's a natural, sobering endpoint to the same story of entropy and the arrow of time that began, right at the start of cosmic history, with the unusually low entropy state that made everything else, stars, planets, chemistry, and eventually us, possible in the first place. So how are we supposed to make sense of all of this? Taken individually, any one of these examples, the Hoyle resonance, the neutron-proton mass gap, the strength of gravity, the amount of dark energy, the smoothness of the early universe, the number of dimensions might be dismissed as a curious coincidence. But taken together, they form a pattern that scientists have been circling around in one form or another for close to 70 years. This general observation, that the fundamental parameters of physics seem oddly well suited for the existence of complexity in life, is usually called the fine-tuning problem, or sometimes the subject of anthropic reasoning, and its modern history stretches back further than most people realize. One of the earliest voices was the physicist Robert Dicke, who in 1957 noticed something curious about the relationship between the strength of gravity and the current age of the universe, an odd numerical coincidence that seemed to require the universe to be at a very particular stage in its development for stars like our Sun and observers like us to exist at all. Dick's argument was an early example of reasoning from our own existence backward to a constraint on the physical parameters of the universe, rather than the more traditional direction of reasoning from parameters forward to predictions. The term anthropic principle itself was coined somewhat later, in 1974, by the physicist Brandon Carter, who wanted to draw a careful distinction between two related but different ideas. What's often called the weak anthropic principle simply observes that whatever conditions we measure in the universe must be compatible with our own existence as observers, since otherwise we wouldn't be here to measure them, which sounds almost too obvious to be worth stating, but turns out to have real explanatory power in cases like Dick's coincidence or Weinberg's later prediction about dark energy. A stronger and much more contested version of the idea goes further, suggesting that the universe must, in some deeper sense, be structured so as to eventually give rise to observers, a claim that a great many physicists find far more philosophically fraught and considerably harder to justify on purely scientific grounds. In the decades since, the topic has been explored at length in academic work, most notably in a lengthy 1986 book by the physicists John Barrow and Frank Tipler, which cataloged an enormous range of these apparent coincidences across physics and cosmology. Later, the astronomer Martin Rees distilled a version of this argument down to just 6 particular numbers in a widely read book aimed at a general audience, arguing that these 6 values alone, spanning things like the strength of gravity relative to electromagnetism and the amount of dark energy in the cosmos, appear to be tuned with a precision that, if any one of them were nudged even slightly, would leave us with a universe incapable of producing anything like the rich structure we observe around us: stars, galaxies, planets, chemistry, and eventually, life. Faced with all of this, there are really only a handful of ways scientists and philosophers have responded, and it's worth walking through them calmly, one at a time, without rushing toward any particular conclusion, because this is genuinely one of those areas where the honest answer is that nobody knows for certain. The simplest response is to say that there's nothing to explain at all. Of course, we observe a universe compatible with our own existence, the reasoning goes, because we couldn't possibly be observing one that wasn't. A universe with no stars, no stable chemistry, and no observers has, by definition, nobody in it to notice how empty and dead it turned out to be. The late writer Douglas Adams once illustrated this kind of reasoning with a small, gently comic thought experiment, imagining a puddle of water that wakes up one morning with the ability to think, looks around at the hole in the ground it happens to be sitting in, and marvels at how perfectly that hole fits its own shape, concluding that the hole must have been made especially for it, never considering the more mundane possibility that the puddle simply took the shape of whatever hole it happened to land in. Maybe, this line of thinking suggests, we're doing something similar. Maybe we simply happen to exist in a universe compatible with our existing, and there's nothing more to say about it. For a lot of scientists, though, that answer doesn't feel fully satisfying. Throughout the history of science, whenever researchers have been tempted to shrug and say that's simply how things are, stop asking why, that attitude has generally not aged well. Curiosity, the refusal to accept unexplained coincidences at face value, has a much better track record. So a second response is to hope that there's a deeper, more complete theory of physics still waiting to be discovered, one that would explain why the constants take the values they do, why the universe began in such an ordered state, why space has 3 dimensions and time has 1, rather than simply taking all of that as a brute, unexplained given. But even this response runs into a subtler difficulty. Suppose physicists eventually did find some deeper mathematical framework that locked every constant into place, leaving no freedom for them to be otherwise. That would be a remarkable achievement, but it wouldn't fully dissolve the puzzle. It would just relocate it one level up. Because then the question becomes, why does the universe follow that particular mathematical framework, out of the vast range of internally consistent mathematical structures that could, in principle, describe some other possible universe instead? The space of imaginable, self-consistent mathematics is enormous, and our universe seems to have settled on one particular slice of it. Explaining away one layer of fine-tuning by appealing to a deeper theory still leaves open the question of why that deeper theory itself looks the way it does. A third response reaches for an explanation outside physics altogether, suggesting that the fine-tuning we observe is evidence of intentional design, that some kind of creator deliberately set the dials of the universe to values compatible with the eventual emergence of life. This is, unsurprisingly, one of the more debated responses among both scientists and philosophers, and reasonable, well-informed people land in different places on it, depending on their broader views about the nature of reality, in ways that go beyond what physics alone can settle. Philosophers who take this argument seriously often frame it in terms of comparing likelihoods, suggesting that a universe finely tuned for complexity is a more probable observation if some kind of intentional design lies behind it, than it would be under the assumption of a single, randomly generated universe with no underlying mechanism supplying variety at all. Critics of this reasoning have raised a number of objections in response, some pointing out that appealing to a designer to explain fine-tuning doesn't obviously simplify the picture, since it introduces a further, even less well-understood entity whose own properties would themselves need explaining, and others drawing on statistical arguments, sometimes discussed under the label of the inverse gambler's fallacy. Questioning whether observing one seemingly improbable outcome truly licenses an inference about some deliberate cause behind it, rather than simply being what any sufficiently long sequence of chance events will occasionally produce. None of these exchanges have settled the argument in either direction, and it continues to be debated actively in academic philosophy of religion and philosophy of science, running on a track that's related to, but ultimately somewhat separate from, the purely physics-based questions about multiverse mechanisms we'll turn to next. A fourth response, and one that a great many physicists find appealing on largely independent grounds, is the idea of a multiverse, an enormous, perhaps even infinite, collection of separate universes, each with its own particular settings for the fundamental constants, its own particular starting conditions, and possibly even its own distinct mathematical laws. On this view, most of these countless universes would be inhospitable, empty of stars, empty of chemistry, empty of anything resembling an observer. But across a sufficiently vast collection, purely by chance, some small fraction would happen to land in the narrow range compatible with complexity and life. And naturally, it's only ever from inside one of those rare, fortunate universes that anyone would ever be around to notice the coincidence and wonder about it. The multiverse idea isn't just a philosophical shrug invented purely to sidestep the fine-tuning puzzle, either. It emerges fairly naturally out of a couple of otherwise independent lines of research in physics. One comes from cosmic inflation, the leading theory describing an extraordinarily brief period of exponential expansion, thought to have taken place in the first sliver of a second after the Big Bang, first proposed by Alan Guth and developed further by physicists including Andre Linde. In many versions of inflationary theory, inflation doesn't simply happen once and then stop everywhere. Instead, it keeps happening in an eternal, self-sustaining way in some regions, spinning off countless separate expanding pockets of space, each one becoming its own effectively separate universe, potentially with its own distinct physical conditions. This picture is often called eternal inflation, and it implies a multiverse almost as an automatic byproduct of the same theory that explains other well-tested features of our own observable universe. A second, largely independent line of reasoning comes out of string theory, a candidate framework for unifying gravity with the other fundamental forces. String theory, in its more fully developed versions, doesn't point to one single, unique way for extra hidden dimensions to be curled up and hidden from our everyday experience. Instead, it seems to allow for an enormous number of mathematically consistent possibilities, each corresponding to a different set of effective physical constants in the four dimensions we actually experience. Physicists including Leonard Susskind have argued that this vast collection, sometimes called the string theory landscape, with estimates for its size running as high as 10 to the 500th power distinct possibilities, could naturally supply the sheer variety of different physical constants that a multiverse explanation for fine-tuning would require. None of this is to say the multiverse is a comfortable or fully settled idea, even among physicists who take it seriously. One persistent worry is what's sometimes called the measure problem, the difficulty of meaningfully comparing probabilities across an infinite collection of universes, since ordinary statistical reasoning tends to break down when you're trying to compare infinities against other infinities. Another well-known worry, sometimes called the Boltzmann brain problem, points out that in an eternally inflating multiverse existing for an unbounded stretch of time, spontaneous fluctuations might, over sufficiently long stretches, be far more likely to randomly assemble a single, briefly conscious, disembodied brain out of chaotic particles than to produce an entire orderly galaxy full of ordinary observers like us. Which is an uncomfortable conclusion for a theory that's supposed to be explaining why ordinary observers exist in the first place. And a broader, more philosophical objection, raised by physicists on more than one side of this debate, is simply that other universes, entirely disconnected from our own, may be permanently unobservable in principle, which raises a fair question about whether multiverse proposals count as testable science in the traditional sense, or whether they sit closer to a kind of physically motivated philosophy. Advocates of the idea tend to respond that inflation and string theory were developed for reasons that have nothing directly to do with fine-tuning, and that a multiverse showing up as a natural consequence of theories built to explain other things is a point in its favor rather than a sign of special pleading, while critics counter that a proposal so difficult to directly test deserves a healthy dose of caution before being treated as an accepted explanation. It remains a genuinely open, actively debated question within physics, not a settled consensus in either direction, and different well-informed physicists land in noticeably different places on how seriously to take it. It's worth stepping back for a moment to place the Hoyle resonance inside its proper historical setting, because it was never really a standalone discovery. It was part of a much larger project to answer one of the biggest open questions in 1950s astrophysics, namely, where do the elements actually come from? In 1957, Hoyle worked together with three other physicists, Margaret Burbidge, Geoffrey Burbidge, and William Fowler, to publish a landmark paper laying out, in careful detail, how nearly every element heavier than hydrogen and helium could be built up inside stars through successive stages of nuclear fusion, and in the case of the very heaviest elements, through the violent conditions found in supernova explosions. That paper is still referred to by astronomers today by the shorthand of its four authors' initials, and it remains one of the foundational works in the entire field of nuclear astrophysics. There's a small historical irony worth mentioning here. In 1983, William Fowler was awarded the Nobel Prize in Physics for this body of work on the origin of the elements, sharing the honor with the astrophysicist Subrahmanyan Chandrasekhar, whose own work on the limiting mass of white dwarfs, the same Chandrasekhar limit that plays a central role in the Type 1, a supernova story we walked through earlier, had gone unrecognized by the Nobel Committee for decades after it was first proposed. Hoyle, despite having pushed the theoretical case that led experimentalists to go looking for the resonance that made carbon production possible in the first place, was not included in that Nobel Prize, a decision that a good number of physicists and historians of science have long considered a curious oversight, given how central his original insight was to the whole story. Hoyle himself, later reflecting on how neatly the physics had lined up to make carbon and oxygen both abundant, was characteristically blunt about how strange he found it. He suggested, somewhat provocatively for a scientist of his era, that a straightforward reading of the underlying physics almost looked as though some kind of guiding intelligence had been deliberately adjusting the rules of nuclear physics to make this outcome possible. It's a striking thing for a working physicist to say, and it's worth noting that Hoyle himself never fully settled on any one explanation for what he was seeing, spending much of the rest of his career exploring unconventional ideas about the origins of life and the universe, some of which found much wider acceptance among his colleagues than others. Martin Rees's version of this argument, the one he narrowed down to just 6 numbers, is worth walking through briefly because it gives a nice, compact tour of how these different kinds of fine-tuning show up across completely different areas of physics. One of his 6 numbers describes the relative strength of electromagnetism compared to gravity, the same enormous mismatch we touched on earlier, roughly 10 to the 36th power, which governs, among other things, how large stars and planets can grow before gravity starts to dominate their structure. Another describes the efficiency with which hydrogen fuses into helium inside stars, a value of a little under 1%, which turns out to control both how long stars live and how effectively the universe manufactures heavier elements. Nudge that efficiency down only slightly, and hydrogen never fuses into anything heavier at all. Nudge it up only slightly, and all the hydrogen in the early universe would have burned away almost instantly, leaving nothing left over to form long-lived stars later on. A third of Rees's numbers describes the overall density of matter and energy in the universe relative to a critical threshold, which determines whether the universe's geometry curves in on itself, curves outward, or lies exactly flat, and our universe appears to sit remarkably close to that flat, critical value, a fact that itself became one of the strongest pieces of supporting evidence for cosmic inflation. A fourth is the cosmological constant we've already spent so much time on. A fifth describes the amplitude of the tiny density fluctuations present in the early universe, ripples in the distribution of matter that were only about 1 part in 100,000, but which needed to be exactly that small, neither much smaller nor much larger, to eventually grow, under the pull of gravity, into galaxies, galaxy clusters, and the large-scale cosmic structure we observe today. Without either staying too smooth to form anything or clumping so violently that galaxies collapse directly into overwhelming numbers of black holes. And the 6th is simply the number of spatial dimensions, which we've also already discussed, 3, a number that permits stable orbits and complex structure in a way that 2 or 4 dimensions apparently do not. Rees's broader point in laying all 6 of these out side by side wasn't that any single one of them, on its own, is unanswerable. It was that the pattern across all 6 together, spanning completely unrelated corners of physics and cosmology, from nuclear efficiency to cosmic geometry to the number of dimensions of space, seemed to demand some kind of unified explanation, rather than being dismissed as 6 unrelated coincidences that all happen to break in our favor independently. It's worth pausing on that idea of vacuum energy for a moment, because even though the size of the discrepancy between prediction and measurement is famously enormous, the underlying concept, that empty space itself carries energy, isn't just a theoretical convenience invented to patch over an awkward gap. It's been tested directly, in a laboratory, through something called the Casimir effect. If you place 2 uncharged metal plates extremely close together in a vacuum, quantum field theory predicts that the plates will experience a tiny attractive force, caused by the way the plates restrict which quantum fluctuations of the vacuum are allowed to exist in the narrow gap between them, compared to the unrestricted space outside. That force has been measured experimentally, and it matches theoretical predictions quite well. So the broader claim that a vacuum is not simply empty in the way our everyday intuition suggests rests on solid experimental ground, even if the specific question of how all of that vacuum energy relates to the dark energy driving cosmic acceleration remains one of the most stubborn unsolved problems in physics. The question of why the early universe started out in such a low entropy, highly ordered state has also been explored quantitatively, not just described qualitatively. The physicist Roger Penrose attempted to estimate just how special that initial state really was by working out roughly how large the space of all possible starting configurations for the universe might be, and then asking what fraction of them would have looked anything like the smooth, low-entropy state we actually find in our own cosmic history. The number he arrived at was almost unimaginably small, so overwhelmingly outnumbered by the alternative, high-entropy, disordered possibilities, that Penrose treated it as one of the deepest puzzles in cosmology, a puzzle that any complete theory of the very early universe, including inflationary theory itself, would eventually need to explain rather than simply assume. There's also a more radical version of the multiverse idea worth mentioning, proposed by the physicist Max Tegmark, sometimes called the mathematical universe hypothesis. Tegmark has argued that every mathematically self-consistent structure, not just every possible arrangement of physical constants within a single set of physical laws, but every conceivable set of physical laws entirely, might correspond to some actually existing universe somewhere, with our own universe simply being whichever mathematical structure happens to correspond to the physical rules we observe. It's one of the more speculative proposals on offer, and it isn't widely accepted as a working scientific theory in the way, say, the standard model of particle physics is, but it illustrates just how far some physicists have been willing to follow the logic of fine-tuning, from adjusting a few numbers within one universe, all the way to questioning whether mathematics itself is the only thing that ultimately needs to exist. On a more grounded, empirical note, physicists have also gone beyond simply reasoning about what might happen if a constant were different, and have actually tried to model it directly. The physicist Fred Adams, among others, has published detailed calculations exploring how stellar structure and stellar lifetimes would change under a wide range of alternative values for gravity, the strong force, and other constants, mapping out which combinations still permit long-lived, stable, fusion-powered stars, and which combinations don't. This kind of work has helped turn fine-tuning from a purely qualitative observation into something closer to a quantitative, mappable landscape, showing not just that our particular combination of constants works, but roughly how large or small the surrounding habitable region of possibility space actually is for each one individually, and in more recent extensions of this research, for several constants varied together at once, which turns out to be a considerably more complicated question than varying them one at a time. It's easy, when talking about all this, to accidentally blur together two different mysterious-sounding ingredients of the universe, dark energy and dark matter, so it's worth taking a moment to keep them separate. Dark energy, the subject of most of what we've covered so far, is the mysterious pushing force driving the accelerating expansion of the universe. Dark matter is something else entirely, an unseen form of matter, distinct from ordinary atoms, that doesn't emit or absorb light, but whose gravitational pull is needed to explain why galaxies rotate the way they do, and why large-scale cosmic structures clump together as quickly and as strongly as they did. Both remain unexplained at a fundamental level, and both are, in their own separate ways, essential ingredients in modern cosmology, But they are not the same mystery, and solving one wouldn't automatically solve the other. Among the specific puzzles the James Webb Space Telescope has turned up, one particularly striking category of objects has become known, somewhat informally, as little red dots, extremely compact, unusually red, surprisingly luminous objects found at great distances, and therefore very early points in cosmic history. Astronomers are still working out exactly what these objects are. Some analyses suggest they may be a previously unknown population of compact, dust-reddened galaxies undergoing an intense early burst of star formation, while others suggest at least some of them could be very young, rapidly growing supermassive black holes, glowing brightly as they pull in surrounding gas, at a stage of growth far earlier than standard models expected such large black holes to have already assembled. Neither explanation is fully settled, and it's entirely possible that different little red dots turn out to be different kinds of objects entirely, but their sheer number, discovered in the relatively short time the telescope has been operating, has added yet another wrinkle to the broader puzzle of how quickly structure managed to form in the young universe, a puzzle that connects back, in a roundabout way, to the same question of just how finely balanced the early conditions of our universe needed to be in order to produce galaxies on the timescale we actually observe. As it happens, both of these mysteries are active areas of observational research right now, using instruments built specifically to pin them down more precisely than ever before. Astronomers have spent the past several years using the James Webb Space Telescope to study extremely distant, extremely early galaxies, and one of the more puzzling findings has been that some of these early galaxies appear to be more massive and more fully formed than standard models of galaxy formation would have predicted for such an early point in cosmic history, a tension that researchers are still actively working through, weighing possibilities that range from adjustments in how efficiently early galaxies formed stars to more fundamental reconsiderations of the standard cosmological model itself. Related to this is an ongoing puzzle called the Hubble tension, named after the same astronomer whose original observation of cosmic expansion we discussed earlier. Different methods of measuring exactly how fast the universe is expanding today, one based on the cosmic microwave background, the faint afterglow of the Big Bang, and another based on directly observing nearby stars and supernovae, keep returning slightly different answers, a discrepancy that has persisted, and if anything, sharpened as measurements have become more precise, rather than resolving itself the way statistical noise usually does. Whether this tension points towards some subtle measurement error still lurking somewhere in one of the two methods, or toward genuinely new physics not captured in our current understanding of dark energy and the early universe, remains an open question that cosmologists are actively working through. Dark energy itself has also come under renewed scrutiny in the past couple of years. Results from the Dark Energy Spectroscopic Instrument, a large ground-based survey mapping the positions of millions of galaxies and quasars to trace the expansion history of the universe in unprecedented detail, have hinted that dark energy might not be a perfectly constant, unchanging quantity after all, but could instead be slowly evolving in strength over cosmic time, an idea sometimes discussed under the label of dynamical dark energy, or quintessence. These results are still being carefully checked, and are not yet considered a settled conclusion, but if they hold up under further scrutiny, they would represent a genuine shift away from the simplest version of the cosmological constant that Einstein originally, and reluctantly, introduced back in 1917, replacing it with something closer to a dynamic field that changes gradually as the universe ages. Meanwhile, two other major instruments are working to sharpen this picture further. The European Space Agency's Euclid Space Telescope, launched in 2023, is conducting an extraordinarily wide survey of galaxies, specifically designed to map out the distribution of both dark matter and dark energy across a large portion of cosmic history, using subtle gravitational distortions in the shapes of distant galaxies to trace unseen mass. And on the ground, the Vera C. Rubin Observatory, newly operational in Chile, is beginning a decade-long survey that will photograph the entire visible sky repeatedly, night after night, specifically designed to catch transient events like Type 1a supernovae in far greater numbers than earlier surveys managed. The very same technique that first revealed cosmic acceleration back in the late 1990s, now being deployed at a scale many times larger than what Perlmutter and Schmidt's teams had access to. Let's go back for a moment to the actual mechanics of how elements are built, because the carbon story we opened with is only the beginning of a much longer chain. The very lightest elements, hydrogen, most of the helium in the universe, and a small trace of lithium, weren't made in stars at all. They were forged in the first few minutes after the Big Bang itself, during a brief window before the expanding universe cooled and thinned out too much for nuclear reactions to continue. This early process, often called Big Bang nucleosynthesis, could only build the very lightest nuclei before conditions became too dilute, which is exactly why the universe needed stars, billions of years later, to slowly cook those light elements into everything heavier. Inside a star, after hydrogen has fused into helium, and helium has fused into carbon through the process we spent so much time on earlier, the story doesn't stop there. In sufficiently massive stars, carbon can go on to fuse into neon and oxygen. Oxygen can fuse into silicon, and silicon can fuse into iron, each stage requiring higher core temperatures than the last, and each stage releasing less usable energy than the one before it. Iron is where this chain of energy-releasing fusion reactions finally comes to a halt, because fusing iron into anything heavier actually absorbs energy rather than releasing it, which is why a massive star's core, upon finishing its silicon burning stage and accumulating a core of iron, can no longer hold itself up against its own gravity and collapses catastrophically, triggering a supernova. It's in the extreme conditions of that collapse and the explosion that follows that elements heavier than iron, including gold, silver, and uranium, get built through rapid neutron capture processes that only exist for a brief moment in the aftermath of a dying star, or, as astronomers have more recently confirmed through direct observation, in the collision of two neutron stars merging together. There's a related piece of stellar physics worth mentioning here too, since it plays a supporting role in the story of dark energy. We mentioned earlier that Type 1a supernovae involve a white dwarf approaching the Chandrasekhar limit before exploding. A white dwarf is what's left over after an ordinary, sun-sized star exhausts its nuclear fuel and sheds its outer layers, leaving behind an extremely dense core, no longer supported by fusion, but instead held up by something called electron degeneracy pressure, a purely quantum mechanical effect arising from the fact that electrons, being a type of particle called a fermion, cannot be squeezed into identical quantum states, and so resist being compressed past a certain point. Regardless of temperature, that resistance is what holds a white dwarf up against the crushing pull of its own gravity, right up until it accumulates enough additional mass, siphoned from a companion star, to cross the Chandrasekhar threshold, at which point even electron degeneracy pressure is no longer enough, and the star detonates in the kind of explosion that gave astronomers their first real evidence for cosmic acceleration. Fine-tuning, as a general worry, actually shows up in particle physics too, in a slightly different guise, quite apart from anything we've discussed about cosmology. Physicists studying the Higgs boson, the particle responsible for giving other fundamental particles their mass, noticed decades before it was actually discovered that quantum corrections to its mass, contributions from all the other particles it interacts with, should naturally push its mass up to an enormous value, far larger than what's actually observed, unless various different contributions happen to cancel each other out with extraordinary, seemingly coincidental precision. This is often called the hierarchy problem, and it's structurally very similar to the vacuum energy problem we discussed earlier, a case where the natural, expected value from theory disagrees wildly with the small, measured value we actually find in nature. For a long time, the leading proposed solution was a theory called supersymmetry, which predicts a whole family of undiscovered partner particles for every particle we already know about, arranged in such a way that their contributions to the Higgs mass would cancel out automatically, without needing any coincidental fine-tuning at all. It was an elegant idea, and it motivated a great deal of the research program at the Large Hadron Collider in Switzerland. But despite years of dedicated searching, no supersymmetric partner particles have turned up in the collider data so far, which has left many particle physicists in an uncomfortable position, forced to either keep waiting for supersymmetry to show up at higher energies than initially expected, consider other, less popular theoretical alternatives, or accept that the small mass of the Higgs boson might, after all, simply be another example of fine-tuning without an obvious underlying mechanism, not unlike the cosmological constant. It's a nice illustration of how this general puzzle, values in nature that look suspiciously precise, keeps resurfacing in different corners of physics, not just in the cosmological examples we've spent most of our time on tonight. It's worth widening the lens one more notch, beyond the fundamental constants of physics entirely, to a related but distinct kind of fine-tuning that shows up much closer to home, on the scale of a single planet. Some researchers, working under what's sometimes called the rare Earth hypothesis, have pointed out that Earth itself seems to benefit from a number of fortunate coincidences quite apart from anything to do with fundamental constants. Our planet orbits within a comparatively narrow band of distances from the Sun, often called the habitable zone, where liquid water can persist stably on a planet's surface without either freezing solid or boiling away. Our unusually large moon, thought to have formed from a giant collision early in Earth's history, appears to help stabilize the tilt of Earth's axis over long timescales, preventing the kind of chaotic wobbling that would otherwise produce extreme and irregular climate swings. This is a considerably more speculative and actively debated area than the fundamental constants we spent most of tonight on, since it's much harder to know how common or rare planets with this particular combination of features actually are elsewhere in the galaxy. But it's a useful reminder that the puzzle of a universe that looks well suited for complexity doesn't stop at the level of physics. It echoes, in a more modest and much less certain way, down to the level of individual planets too. Not every physicist who takes fine-tuning seriously reaches for eternal inflation or the string theory landscape as the mechanism generating variety across universes. The physicist Lee Smolin proposed a rather different idea back in the 1990s, sometimes called cosmological natural selection, suggesting that new universes might be born inside black holes, on the other side of their central singularities, with the physical constants in each newly formed universe coming out slightly, randomly mutated from those of the parent universe that produced it. Smolin's proposal had an appealing feature, because unlike a purely random multiverse where habitable universes are simply rare, lucky exceptions, this mechanism would, over successive generations, tend to favor universes that are especially good at producing black holes, since those are exactly the universes that get to reproduce most prolifically, in a manner loosely analogous to natural selection in biology. Whether a universe that's good at making black holes also tends to be good at making stars, chemistry, and life is a separate and more difficult question, and critics have raised a number of technical objections to the proposal, but it remains an interesting example of physicists reaching for genuinely different kinds of mechanisms to explain the same underlying puzzle. It's also worth being honest that not everyone in physics is comfortable leaning on multiverse reasoning to begin with, even setting aside the specific mechanism. The physicist Paul Steinhardt, who was himself one of the original architects of inflationary theory back in the early 1980s, later became one of its more prominent critics, arguing that once you allow eternal inflation to spin off a limitless variety of separate pocket universes, each with different properties, the theory stops making any sharp, testable predictions at all. Since almost any observed outcome could be explained away by supposing, we simply happen to live in whichever corner of the multiverse produces that particular result. From this point of view, an explanation flexible enough to accommodate any possible observation risks, not really explaining anything in the falsifiable, predictive sense that's usually considered central to how science works. Proponents of eternal inflation have pushed back on this criticism in various ways, arguing that the theory still makes distinctive predictions about the broader statistical properties of our own observable universe, even if it can't pin down every constant with certainty. But the disagreement between these two camps remains a genuinely live, unresolved argument within the physics community, not a dispute that's been cleanly settled one way or the other. There has also been at least one attempt to look for direct observational evidence of other universes colliding with our own, rather than relying purely on theoretical argument. If eternal inflation is correct, and our universe is one bubble among countless others, it's conceivable that a neighboring bubble universe might have collided with ours at some point in the distant past, leaving behind a faint, characteristic imprint in the cosmic microwave background, the ancient light left over from the early universe. Researchers have searched the detailed maps of that background radiation, produced by satellites including the European Space Agency's Planck mission, for exactly this kind of signature. So far, no confirmed evidence of a bubble collision has been found, though the search itself is a nice example of physicists trying to find some genuinely observable consequence of multiverse theory, rather than leaving the whole idea permanently outside the reach of experiment. It's worth going a little further back, to where cosmic inflation came from in the first place, because it wasn't originally proposed to explain fine-tuning or motivate a multiverse at all. In 1980, the physicist Alan Guth was trying to solve two much more down-to-earth puzzles about the early universe. One was called the horizon problem, the observation that regions of the cosmic microwave background on opposite sides of the sky have almost exactly the same temperature, even though, under the standard picture of the expanding universe without inflation, those regions would never have been close enough together, or old enough, for light or any other signal to have traveled between them and equalized their temperatures. The other was the flatness problem, the puzzle of why the overall geometry of the universe today looks so close to perfectly flat, when even a very slight deviation from flatness in the extremely early universe should have been dramatically amplified over billions of years of subsequent expansion, making a universe as flat as ours, at this late stage, seem like an enormous coincidence unless something had specifically flattened it out early on. Guth's proposal was that the very early universe went through an extraordinarily brief period of exponential expansion, stretching space so violently and so quickly that any initial curvature would have been smoothed out almost perfectly flat, in much the same way that the surface of a balloon looks flatter and flatter the more you blow it up. And any regions that started out in causal contact before inflation began would then be stretched far enough apart to explain the uniform temperature we see across the whole sky today. It was an elegant solution to two very specific, very technical cosmological puzzles, and it's only as later physicists worked out the detailed mathematics of how inflation would actually play out that the eternal, self-replicating version of the theory emerged, seemingly as an unavoidable consequence, rather than something anyone had originally set out looking for. That's part of why physicists sympathetic to eternal inflation tend to view the multiverse it implies as a serious hypothesis worth taking on its own terms, rather than a convenient invention cooked up specifically to explain away fine-tuning after the fact. The cosmic microwave background itself is worth a brief detour, since it keeps appearing throughout this story as a kind of all-purpose measuring tool. It was discovered almost by accident in 1964 by two radio astronomers, Arno Penzias and Robert Wilson, who kept picking up a faint, uniform hiss of radio noise in their antenna that they couldn't get rid of, no matter how carefully they cleaned the equipment or accounted for other sources of interference. It turned out to be the faint, cooled remnant of light released roughly 380,000 years after the Big Bang, when the universe had expanded and cooled enough for atoms to form and for light to finally travel freely through space, rather than constantly scattering off a hot, dense soup of charged particles. That faint glow, now stretched by cosmic expansion into microwave wavelengths, still fills the entire sky today, and detailed satellite maps of its tiny temperature variations have become one of the single richest sources of information about the early universe, used to pin down the age of the universe, the relative amounts of ordinary matter, and dark energy, and the overall geometry of space, all from studying the subtle pattern of hot and cold spots in that ancient afterglow. It's also worth mentioning that not every physicist agrees the accelerating expansion of the universe necessarily requires a new form of energy at all. An alternative family of explanations, sometimes grouped together under the label of modified gravity, suggests that instead of adding a new substance like dark energy into the universe, we might need to modify Einstein's equations of general relativity themselves, so that gravity behaves slightly differently on the largest cosmic scales than it does within a single galaxy or solar system. Various specific proposals along these lines have been explored over the years, and most have run into some difficulty matching the full range of observational evidence as precisely as the standard picture of dark energy plus dark matter does. But the underlying question, whether cosmic acceleration reflects a genuinely new component of the universe, or a subtle correction needed in our theory of gravity itself, remains a live one. And it's part of why observatories like Euclid and the Vera Rubin Observatory are designed to gather such large, precise data sets, since distinguishing between these competing explanations requires exactly the kind of detailed, large-scale, high-precision measurements those instruments are built to provide. If dark energy does turn out to be a slowly evolving field rather than a fixed constant, the exact way it evolves over time would have real consequences for the far future of the universe, beyond the general picture of slow cooling and spreading out that we touched on earlier. Physicists often describe the behavior of dark energy using a parameter, usually written as W, that compares its pressure to its density. A pure cosmological constant, of the kind Einstein originally introduced, corresponds to one particular fixed value of that parameter, and under that scenario, the accelerating expansion continues smoothly and indefinitely, gradually pulling galaxies apart from one another, without ever tearing apart smaller, gravitationally bound structures like individual galaxies, solar systems, or planets themselves. But if dark energy instead behaves as a genuinely dynamic quintessence field, with its strength changing over cosmic time in the way some recent large-scale galaxy surveys have tentatively suggested, a wider range of future outcomes becomes possible. In one particularly dramatic scenario, sometimes called the Big Rip, the repulsive effect of dark energy could keep strengthening over time to the point where it eventually overwhelms not just the gravity holding galaxies together, but even the forces holding solar systems, planets, and eventually atoms themselves intact, tearing the universe apart at every scale in a finite amount of time, rather than the slow, gentle heat death that a simple constant would produce. Current data doesn't point clearly toward this more dramatic outcome, and a great deal of observational work over the coming years, from the same instruments already mentioned, will be needed before physicists can say with any real confidence which of these long-term futures our universe is actually headed toward. Stepping back from the details of any single mechanism, it's worth being honest about where all of this actually leaves us, scientifically. At the moment, there are several serious candidate explanations on the table for why our universe's fundamental constants look so unusually well-suited to complexity, ranging from a yet undiscovered deeper theory that would lock every constant into place without any remaining freedom, to some version of a multiverse spread across an enormous variety of separate universes, to modifications of gravity or dark energy that might reduce just how finely tuned certain numbers actually need to be, to the more purely philosophical possibility that there's simply nothing further to explain beyond the fact that observers can only ever find themselves in a universe compatible with their own existence. None of these has been established as clearly correct, and a fair amount of intellectual honesty is required to sit with that uncertainty, rather than rushing toward whichever explanation happens to feel most satisfying. Philosophers of science have their own name for a version of this puzzle, sometimes framing it in terms of what's called an observer selection effect, the general principle that any reasoning based on our own existence has to carefully account for the fact that we could only ever have found ourselves in circumstances compatible with us existing at all, quite apart from how common or rare such circumstances actually are across the full range of possibilities. The philosopher Nick Bostrom has written at length about how tricky this kind of reasoning can get, particularly once you start trying to compare probabilities across genuinely different, causally disconnected universes, rather than simply different regions of one single universe, which is part of why the measure problem we touched on earlier, the challenge of meaningfully comparing infinities of different universes against each other, remains such a persistent headache for physicists and philosophers working on multiverse cosmology, rather than a minor technical footnote that will obviously get resolved with more careful mathematics down the line. There's another active line of research worth mentioning, closely related to everything we've covered about constants needing to sit at very particular values, and that's the question of whether those constants have always held perfectly steady, or whether they might drift, ever so slightly, over cosmic time. If a constant like the strength of electromagnetism, often expressed through something called the fine structure constant, turned out to change even a tiny amount over billions of years, that would have enormous implications for everything we've discussed tonight, since fine-tuning arguments generally assume the values we measure today are the same values that applied throughout cosmic history. Physicists have tested this by studying light from extremely distant quasars, ancient and extraordinarily bright objects, whose light has traveled for billions of years before reaching our telescopes, passing through clouds of gas along the way that absorb very specific wavelengths of light depending on the precise values of atomic constants at the time and place that absorption happened. By comparing those ancient absorption patterns to the equivalent patterns measured in laboratories today, researchers can place tight limits on how much, if at all, those constants could have changed over the intervening billions of years. The results so far have been reassuringly boring, in the best possible sense for anyone trying to understand today's universe using today's physics. Most careful studies have found no convincing evidence that the fine structure constant, or other closely related constants, have changed by any statistically significant amount over the observable history of the universe, though a handful of studies have reported tentative hints of tiny variations in certain directions across the sky, hints that have not been confidently confirmed by independent follow-up work, and remain a subject of ongoing observational effort rather than a settled result either way. Similar tests have also been carried out much closer to home, using extraordinarily precise atomic clocks here on Earth, comparing their ticking rates over years of continuous operation to search for any drift in fundamental constants on a much shorter timescale. And these too have so far found no confirmed variation, tightening the constraints even further. There's also a deeper theoretical question lurking underneath everything we've discussed tonight, which is whether physicists will ever find a single, complete theory capable of unifying gravity with the other fundamental forces, a long-sought goal sometimes referred to, perhaps a little too grandly, as a theory of everything. String theory remains the most extensively studied candidate, though as we touched on earlier, its tendency to allow for an enormous landscape of possible low-energy physical laws, rather than pointing toward one single, uniquely correct set of constants, has made it a source of both excitement and frustration within the field. A different candidate approach, called loop quantum gravity, takes a rather different starting point, attempting to directly quantize space and time themselves into discrete units, without necessarily requiring the extra dimensions or landscape of possibilities that string theory involves, though it has its own significant unresolved challenges, particularly in recovering ordinary, smooth spacetime and standard particle physics at everyday energy scales. Neither approach has yet produced a testable prediction that has been confirmed in an experiment, which is part of why unifying gravity with quantum mechanics remains one of the most significant open problems in all of physics, entirely separate from, but closely intertwined with, the fine-tuning puzzle we've spent tonight exploring. There's one more technical result worth mentioning here, from the study of eternal inflation itself, which complicates the picture in an interesting way. A theorem developed by the physicists Arvind Borde, Alan Guth, and Alexander Vilenkin shows that, under fairly general assumptions, any universe that has been expanding on average throughout its history, which includes essentially all versions of eternal inflation, cannot be extended infinitely far into the past. In other words, even an eternally inflating multiverse, endlessly spinning off new pocket universes into the future, still appears to require some kind of definite beginning further back in time, rather than having existed forever without a starting point. This result surprised many physicists working on eternal inflation, since one might have hoped that eternal inflation could sidestep the question of a cosmic beginning entirely, and it means that even the multiverse as a whole still leaves open the deeper question of where it, and its underlying physical laws, ultimately came from in the first place, an unresolved question that simply gets pushed back one more level. Much like the earlier worry about explaining our particular set of physical laws by appealing to some deeper mathematical structure. There's a cautionary story worth telling here too, about just how carefully claims in this area need to be checked before they're accepted, since the history of inflationary cosmology already includes one well-known false alarm. In 2014, a team of researchers working on an experiment called BICEP-2, based at the South Pole, announced what they described as a detection of a particular pattern of polarization in the cosmic microwave background, a pattern that, if genuine, would have been strong evidence for gravitational waves generated during cosmic inflation itself, exactly the kind of signal that later, more sensitive experiments are still hoping to find. The announcement made headlines around the world, and for a brief period, it was treated as one of the most significant cosmological discoveries in decades. But within about a year, a careful joint analysis combining the BICEP-2 data with additional measurements from the European Space Agency's Planck satellite showed that the signal could be almost entirely explained by ordinary dust within our own galaxy, scattering and polarizing light in a way that closely mimicked the pattern the team had been hoping to see, rather than by any genuine signal from the early universe. The claimed detection was quietly withdrawn, and the episode has since become something of a standard cautionary example within cosmology, a reminder of how easily a real, carefully measured signal can still be misattributed to the wrong underlying cause, and why extraordinary claims in this field tend to be treated with real caution until they've been checked, independently, several times over, by more than one team using more than one instrument. If any of this has caught your interest enough to want a longer, slower treatment of the same territory, There's a well-regarded book called A Fortunate Universe, written jointly by the astrophysicists Geraint Lewis and Luke Barnes, that walks through many of these same examples in considerably more mathematical depth. It's a book with an interesting internal tension built right into its authorship, since one of its two writers approaches the subject as an atheist, and the other as a theist, and the book is candid about that disagreement rather than papering over it, letting the two of them lay out the same evidence side by side while reaching somewhat different conclusions about what it ultimately means, which feels like an appropriately honest way to handle a topic that, as we've spent this whole time exploring, doesn't currently have a single, settled answer that all physicists agree on. Sitting with all of this for a while, it's worth noticing how differently this topic behaves compared to most other scientific questions. Most of physics eventually resolves. You measure something carefully enough, you run the experiment enough times, and eventually the data settles a disagreement one way or another. The fine-tuning puzzle doesn't seem to work that way, at least not yet, and maybe not ever, since large parts of it hinge on comparing our one observable universe to other universes we may never be able to directly observe, no matter how sophisticated our telescopes eventually become. That's an unusual position for physics to find itself in, more comfortable in some ways in the territory of philosophy, where a question can remain genuinely open, discussed carefully and rigorously for generations, without any expectation of a tidy resolution arriving on any particular timeline. That doesn't make the question any less worth asking, though. If anything, it might make it more worth asking, precisely because it sits at the boundary of what current physics can settle, forcing us to think carefully about the difference between what we can measure, what we can infer, and what may simply remain, for now or perhaps permanently, a matter of reasoned speculation rather than confirmed fact. There's an interesting tension worth sitting with here, connecting everything we've discussed tonight to a completely different, equally unresolved puzzle, usually called the Fermi paradox, named after a comet attributed to the physicist Enrico Fermi. Given how old and how large the universe is, and given that the physical constants of our universe appear to be so well suited to producing stars, planets, and complex chemistry, a natural question follows. If the conditions for life are so finely tuned, and yet apparently satisfied throughout a universe containing hundreds of billions of galaxies, each with hundreds of billions of stars, where is everybody? No confirmed evidence of life beyond Earth, intelligent or otherwise, has ever been found, despite decades of searching. Fine-tuning arguments on their own don't resolve this puzzle, and if anything they sharpen it, since they suggest that the physics underlying our universe is, at least in the narrow sense of permitting complexity to exist at all, unusually generous rather than unusually stingy. Resolving the tension likely depends on factors fine-tuning doesn't directly address. Questions like how difficult it actually is for simple chemistry to cross over into self-replicating life in the first place. How often single-celled life goes on to develop the kind of complexity found in multicellular organisms, and how long technological civilizations typically last once they arise, none of which current science has a confident answer to. It's a nice illustration of how fine-tuning, even if fully explained one day, would only address one piece of a much larger, layered puzzle about our place in the universe, rather than settling the whole question of how common or rare we ultimately are. So where does that leave things as of right now? A fair summary would go something like this. We know with real confidence that a number of the fundamental constants and initial conditions of our universe sit in narrow ranges that permit the kind of complexity needed for stars, chemistry, and eventually life. That part isn't seriously disputed. What remains genuinely unresolved is why. We don't know whether a deeper, more complete theory of physics will eventually explain these values as logical necessities rather than free parameters, closing off the puzzle entirely, or whether such a theory, even if found, would simply relocate the mystery one level further down, into the question of why that particular deeper theory holds instead of some other one. We don't know whether the multiverse, in any of its various proposed forms, from eternal inflation to the string theory landscape, to Smolin's black hole reproduction idea, actually exists, or whether it will ever be possible to gather direct observational evidence for or against any of these proposals, given how much of the reasoning depends on universes that may be permanently beyond the reach of any telescope we could ever build. We don't know still what dark energy actually is at a fundamental level, whether it's a fixed cosmological constant exactly as Einstein reluctantly introduced back in 1917, a slowly evolving quintessence field as some recent large-scale surveys have begun to hint, or a signal that our understanding of gravity itself needs revision on the largest cosmic scales. And we don't know whether the small mass of the Higgs boson, sitting so much lower than naive calculations would suggest, points towards some undiscovered particle physics waiting to be found at higher energies than the Large Hadron Collider has yet reached, or whether it, too, is simply another example of an unexplained fine-tuned number, with no tidy mechanism behind it at all. None of these are questions sitting quietly on a shelf, either. Research addressing pieces of this puzzle is actively underway right now, across a whole range of different instruments and approaches. The Dark Energy Spectroscopic Instrument continues gathering data that may eventually confirm or rule out the hints of evolving dark energy that recent analyses have turned up. The Euclid Space Telescope and the Vera Rubin Observatory are both, this year, in the process of building up the kind of enormous, precise catalogs of galaxies and supernovae needed to distinguish between competing explanations for cosmic acceleration, work that will likely take years to fully mature into confident conclusions. The James Webb Space Telescope continues turning up more of those unexpectedly massive early galaxies, data that cosmologists are still in the middle of reconciling with standard models of how quickly galaxies should be able to form after the Big Bang. Physicists at the Large Hadron Collider continue searching, at ever higher energies and with ever larger datasets, for any sign of the new particles that might resolve the hierarchy problem, whether that turns out to be some form of supersymmetry or something nobody has yet proposed. And theorists working on string theory, loop quantum gravity, and a handful of less mainstream approaches continue trying to find some genuinely testable prediction that could distinguish between these competing frameworks for unifying gravity with the rest of physics, a search that has now stretched across several decades without a clear resolution in sight. There is even a planned space-based gravitational wave observatory, expected to launch in the next several years, that some theorists hope might eventually be sensitive enough to detect a background of gravitational waves left over from cosmic inflation itself, which would offer a genuinely new and independent line of evidence bearing on how inflation actually unfolded, and by extension, on whether the eternal, multiverse-generating version of the theory is on the right track. What makes this particular corner of physics worth returning to again and again isn't the promise of an approaching resolution. It's something closer to the opposite. Every serious answer anyone has proposed so far, a deeper theory, a multiverse, a modification to gravity, an appeal to design, or simply the observation that we couldn't be having this conversation in a universe where the numbers didn't work out, comes with its own genuine strengths and its own genuine, unresolved difficulties, and reasonable, careful, well-informed physicists currently disagree, sometimes quite firmly, about which of these possibilities deserves the most confidence. There's a nice way of putting this idea that gets attributed to the physicist John Wheeler, the thought that the more our collective island of scientific knowledge grows, the longer the shoreline separating what we know from what we don't seems to become, since every answered question tends to open up several new ones along its edges. Fine-tuning feels like a particularly vivid example of that pattern in action. working out why stars make exactly enough carbon and exactly enough oxygen, or why the neutron is only very slightly heavier than the proton, hasn't closed off a chapter of physics so much as it's revealed just how much shoreline is still out there, waiting. So it seems fitting to end without tying this into a neat bow, since the honest state of the science doesn't currently offer one. Somewhere out past the edge of the solar system, past the outer planets, past the faint, cold objects drifting through the dark, the same handful of physical constants that let a star like our sun burn steadily for billions of years are quietly doing exactly what they've always done, and doing it, as far as anyone has been able to determine, with no more explanation than the fact that we happen to be here to notice it, turning 3 helium nuclei into 1 atom of carbon. At almost precisely the rate the universe seems to require, for reasons that remain, for now, one of the more genuinely open questions in all of science. And there's something rather calming in its own way about letting a question like that simply stay open, unresolved, and quietly interesting as you drift off tonight.